probability is a very large field of study, and there's many directions you can go once you got the basics of theoretical and frequency-based probability down. So really, the idea this week is to see two of the big areas you could go that are most applicable to everyday business situations and other applications in general. So we saw Markov chains. Another thing we could talk about is random variables. And the big idea here is expected value, which is something we'll hit upon too. Really, all a random variable is a way of assigning a number to events or outcomes in your sample space. So these random variables can be either discrete or continuous. And so the difference is a discrete random variable will have gaps between the possible values. So a discrete random variable could be something like 1, 2, 3, or 4, but not 1.5, not 2.7. Whereas continuous random variable can be a range of values, something like 1 to 10, any value in between. For our study, we'll only see discrete random variables. If you take a course like business statistics or probability and stats, problem stat, you'll see continuous random variables as well, and both are studied quite a great deal. But for us, we've mainly been seeing discrete random variables already. We just haven't talked about them in that perspective, but really we've been dealing with that because we've been often dealing with counts. So what I want to do is use an example like probability questions we've done before and try to figure out what the probability distribution would be. We'll explain what that means and what a random variable might look like here. And so this is a classic type of counting probability problem that we've seen before. We have a group with 6 men and 7 women. 2 were selected for a committee, and X is going to represent the number of women selected. And so the first question is this discrete or continuous? So this is definitely discrete. Because when you count things, you can't count by 1.5 for most counting that we do, for the type of counting that we do when we're doing something like this. So this is definitely discrete. What are the possible values? So if you select 2 people out of this group, you might end up with no women, right? It's possible to select 2 men. Or you might end up with 1 woman and 1 man, but X only counts the number of women, so it'd be 1. Or you could end up with 2 women selected. And then the next question says, what's the probability distribution of X? So the probability distribution of X will be a table representing all the possible values of X, which are 0, 1, and 2, and all of their probabilities. And we'll talk about some properties of that in a moment. So in other words, it's the probability X equals 0, the probability X equals 1, and the probability X equals 2. And so we got to find those probabilities to actually make the probability distribution. And a probability distribution gives you a way of seeing the whole situation at one glance, and also of understanding ideas like expected value that we'll talk about soon. And so the probability distribution of this X, well, first thing we got to do is find the probability X equals 0. So as you can see, having random variables really is just a way of simplifying our thinking about situations we've already dealt with. X equals 0 is really just the probability that no women are selected, which is really just the probability that 2 men are selected, right? And so in this particular case, we say, well, how many ways could 2 men be selected? Well, you're selecting from 6, you're selecting 2. And overall, you're selecting from 13, 2 people, right? So it'd be 6 choose 2 over 13 choose 2, which if you put in your calculator is 0. We'll round to say 3 decimals, 192. Right? So I can add that to my table. So 0.192. All right, I'm going to skip 1 for a minute. I'll explain that in a minute. Let's look at 2. X equals 2. That's just the probability that 2 women are selected. And so in this case, that would be 7 choose 2 over 13 choose 2. Okay, so I can put that in my calculator, and I get 0.2, let's say 69 to be consistent. So 0.269. All right, now I skipped over 1. There's a couple reasons for that. First of all, 1 is going to be more difficult because that's 1 woman and 1 man. So slightly more calculation. Second of all, once I have almost all the pieces of a probability distribution, I can actually use the idea of what a probability distribution is to help me find the remaining value. So a probability distribution is supposed to be all the possible values of X and all their probabilities, right? If all possibilities are taken into account, then the total should be 1. So whatever that value is, when I add it up with 0.192 and 0.269, it should be 1. In other words, if I take 1 and subtract 0.192 and subtract 0.269, I should get the remaining value, which I do. I get 0.539. And there's my probability distribution. So looking at this, what I can tell is that most likely you're going to end up with one man and one woman in this group, which makes sense because you're picking two people, and it's almost evenly split. I can see that it's slightly more likely that you'll pick two women as opposed to two men, but that also makes sense. And so maybe you can see how this would be useful for a very large experiment where you have many, many possibilities as far as understanding what's going on. So again, a probability distribution is a way of looking at all the possibilities. If we were looking at a continuous random variable instead of a table, this would actually be a curve. Very, very different. Now, another way we could approach this is dealing with data where the counting's already done for us. And so in this example, we're given the number of computers owned and number of households based on a survey. So they went around asking people, how many computers do you own? And for example, 85 people said, oh, we have one computer in our household. And so looking at this, I ask for the probability distribution of x, where x is the number of computers owned. So as you can see, x can only be 0, 1, 2, or 3, right? And so now we just got to figure out the probability of x. Now I want to put decimals in here. I want to put it in a nice simplified form. So what I need to do is figure out the probability x equals 0, x equals 1, etc. The probability x equals 1 would be the probability of picking somebody out of this group such that they have no computers, or excuse me, the probability x equals 0 would be the probability of picking somebody out of this group such that they own no computers. So that would be 15 out of the total, right? And if you add up the total real quick, you get 15 out of 150. So when you divide, you end up with 0.10. So you can round however you would like. So this would be 85 out of the total. I get 0.57. 45 out of the total. I get 0.30. And 5 out of the total. Get 0.03. So this is really straightforward as far as finding the probabilities because most of the work's already been done for us. And if you add up, you'll see that it adds up to 1. So this probability distribution represents what would happen if you were to randomly pick somebody from this group. Most likely what would happen, looking at this, I can see most likely somebody from this group has one computer in their household. Now if I was to think of in terms of an average, it'd probably be between 1 and 2 because most of our probability is around 1 and 2, right? So if I was to think of this as a graph, I would have most of my probability here and here. So maybe an average would be something like 1.5, even though you couldn't get 1.5 computers in a household, the average would average out if you were to keep picking people. Now the question is, how can I make that more mathematical? How can I make that a little more stringent? And so understanding this a little bit deeper requires the use of something called expected value. And so expected value is the long run average. In this example, what it would represent is if you were to continue picking people, so pick somebody, how many computers do they have? Pick somebody, how many computers do they have? And average out all the numbers, the value you would get would be the expected value. And as we saw, it'd probably be between 1 and 2 because that's where most of the probability was. The formula for expected value is the sum of all the x's times the probability of the x's. So you take each x, you multiply times its probability, and you add all of these up. You should absolutely know this formula. So let's see how it looks when it's applied. For the previous example, I'll jot down what our probability distribution looked like. We're talking about picking people. They had either 0, 1, 2, or 3 computers in their household. It was 10% for the 0, approximately 57% for 1, approximately 30% for 2, and approximately 3% for 3. So the expected value would represent, again, if you repeatedly picked people, on average, how many computers would they have? And so E of x would be 0 times 0.1 plus 1 times 0.57 plus 2 times 0.3 plus 3 times 0.03. So this is a quick calculation. And I get 1.26. So this means that I would expect, on average, for each household to have about 1.26 computers. Kind of a strange way to say it, right? This is kind of like the idea of a household typically has 2.3 kids, right? No particular household has that many kids. No particular household has 1.26 computers. This is just the long-run average if you were to look at many, many households and average the number of computers. So this gives me a way of looking at experiments that are very large and data that's very large and understanding how it behaves. Expected value also has a lot of applications in things like insurance, and it's very popular to use in gambling. When people are trying to understand poker hands and things like that, they'll use expected value quite a bit. We won't quite see that kind of stuff, but I will show you another example that's a little bit different, just so you can see one example that's not as applied as the others. So this example says we're going to select a number at random from this group of numbers right here. The random variable x represents the remainder when the number is divided by 3. So find the probability distribution and the expected value. There can only be one expected value of x. All right, so first of all, I got to figure out the possible values of x to figure out my probability distribution. All right, so it's the remainder when you divide by 3. So when you divide 3 by 3, there's no remainder. 4 by 3 would be remainder 1. 5 divided by 3 would be remainder 2. And then 6 divided by 3 would be 2 times, but remainder 0, so that stays. Remainder 1, remainder 2. 9 is divisible by 3, so there would be no remainder. And 10, remainder would be 1. So the only possible values are 0, 1, and 2. So now we got to figure out their probabilities. So the underlying experiment is picking a random number from here. There are 1, 2, 3, 4, 5, 6, 7, 8 numbers. 1, 2, 3, 4, 5, 6, 7, 8. Okay, I want to make sure. So all these probabilities are going to be out of 8. So I'm going to do my work over here. So probability x equals 0 is going to be something over 8. All right, so how do I get a remainder of 0? It's when I divide by 3 and it's already divisible by 3. So that could happen with this if I divide 3 by 3, 6 by 3, or 9 by 3. So this would be 3 out of 8, which is about, or actually exactly, 0.375. All right, how do I get a remainder of 1? It's when you're 1 more than something divisible by 3, so that would be 4. So 1, 2, and 3. This would also be 3 out of 8. And what's probably x equals 2? So the only way you could get 2 is if you're 2 away, 2 above something that's divisible by 3. So that would be either 5 or 8. So there's 2 out of 8 ways that could happen. Of course, that's 1/4. That's 0.25. Right? So if I was to write this out, this would be 0.375, 0.375, and 0.25. So if you were to kind of think about what would the average, if you were to just pick one of these numbers, what would be the remainder, you'd think most often to be either 0 or 1, right? That's where most of our probability is. So if I was to think what would I expect the expected value to be, probably somewhere between 0 and 1. It will probably get pulled a little bit by this probability at 2. So finally, the expected value, so this is my probability distribution, answers the first part of the question. Expected value would be 0 times 0.375 plus 1 times 0.375 plus 2 times 0.25. Okay, so that comes out to 0.375 plus 0.5 if you really think about it. In other words, 0.875. You can never have a remainder of 0.875. This is saying that if you were to do this over and over again, so you pick a number, what's the remainder? Pick a number, what's the remainder? You get a bunch of 0, 1s, and 2s, right? Those are the only possible values. If you average all of those out, you'll get 0.875. So that means most often you'll see 0 and 1 as your remainder. You may say, where could this be applied? There's plenty of computer science applications for something like this. And I thought it'd be interesting to look at this since your textbook looks more, of course, at the business applications, which you should study as well. But it shows you really that we can apply expected value to places you would never think would make sense.